What's going on, everybody? High Peak Education, physics problem, rolling motion coming at you again. So, let's take a look. A ball with an initial velocity of 8.00 meters per second rolls up a hill without slipping. Treating the ball as a spherical shell, that's a hollow sphere, and this is the rotational inertia equation, I equals 2/3 mr squared. Calculate the vertical height it reaches. B. Repeat the calculation for the same ball if it slides up the hill without rolling. Okay, so the idea is that the angle of the incline I don't think is going to matter because, let's just kind of sketch the sphere here for a second. So here's a sketch of this ball rolling up this hill, and we want to know what this final height is. And no matter what this angle theta is, we note that via conservation of mechanical energy, we know that gravity is a conservative force which is path independent. That's why we can define a so-called potential function, and it's not going to matter what this theta is. It's either a very long incline and the same final height, or a very steep incline with the same final height. But either way, the final height should be the same. We know the initial velocity of the ball, that's the initial linear velocity, is 8.00 meters per second, and we know that this is a spherical shell. So it's something like this, okay? And we have this for the initial velocity, VI. Now that's the VI of the center of mass, okay? So the idea is that any angular velocity this has, because when this thing is rolling, it has linear and rotational kinetic energy. So it has kinetic energy of the center of mass and kinetic energy of spinning. So whenever we see the angular velocity, say initial, we're going to put in the linear velocity divided by the radius. So this is converting rotational to linear. So let's see what happens. We're going to use, again, the conservation of mechanical energy. So at the bottom here, I think we only have kinetic energy initial. And at the top here, we only have gravitational potential energy final when the ball stops. So the initial kinetic energy is the same thing as the initial translational kinetic energy plus the initial rotational kinetic energy. And again, that's equal to the final gravitational potential energy. So if we write this out, this should be 1/2 mass of this ball times this initial velocity squared, that's the linear velocity, plus 1/2 the rotational inertia of this ball, times the initial angular velocity squared, is equal to mgh final. Oh, and then by the way, this m is the same as the big M, gh final. Okay, all looks good. Now, let's go ahead and put in the equation for the rotational inertia, and then the equation for the angular velocity. So then, again, this is going to go right in here, and then this angular velocity goes in here. So we have 1/2 mv initial squared plus 1/2, and then we times by 2/3 mr squared times, this is going to be v initial squared over r squared, and then equals mgh final. Okay, all looks good. Notice that all these masses will cancel. In other words, this is independent of mass. And notice that these radii will cancel. So it's not going to matter what the radius of this thing is. It turns out that all solid spheres, all hollow spheres, will make it to the same height, no matter what their radius or mass is, interestingly enough. So let's work out the fractions and everything here. We have 1/2 v initial squared plus 1/2 times 2/3, I think, is 1/3. Then v initial squared is equal to gh final. Now let's see, we have to do fraction addition. So 1/2 plus 1/3, I think that's 3/6 plus 2/6. I think that's 5/6 v initial squared over g. And we could clean this up to be 5 v initial squared over 6g, just to make it not look like a complex fraction. is h final. Okay, so let's put those numbers in. So we need 5 times the initial velocity of 8.00 meters per second, and we square that, and we divide that by 6 times the gravitation constant, 9.8 meters per second squared. Okay, so let's get this value approximately. So let's go alpha, F1, and numerator over denominator, fraction stack. Let's go 5 times 8 squared, and we'll divide that by 6 times 9. Okay, so this should be 5.44, and that's meters. Let's write this down. 5.44 meters. Okay, so this solves part A. Now, part B, repeat the same calculation if the ball slides up the hill without rolling. Well, if it slides up the hill without rolling, I think the translational kinetic energy initial should just equal the gravitational potential energy final. There's no rotation term. All the energy is that of the center of mass becomes potential energy. Now, because it's going to have less kinetic energy, because it's not rolling, it's going to not make it as high. So we'll have 1/2 mv initial squared equals mgh final. These masses cancel, and then now we're going to have h final is, let's see, v initial squared over 2g. Notice this is effectively a half. This is effectively 5/6. I think 5/6 is larger than the half, so the ball won't go as high. So this is v initial, that's 8.00 meters per second, and we square, time divided by 2 times 9.8 meters per second squared. All right, so let's get this value in the calculator. So we can use just what we had before, but let's make the numerator up here, instead of a 5, let's just make it a 1. And instead of downstairs being a 6, let's just make that a 2. That's a 1/2 factor. Okay, so we should have 3.27, that's meters. So you see that having rotation makes the ball go higher, because if it has energy locked up in rotation as well as translation, the ball will actually go higher. So this is how we solve these conservation of energy problems with rolling objects. Thank you very much for watching this video. Please smash that like button if you enjoy this content. Please share this video and subscribe to the channel to grow the channel. I look forward to seeing you in the next video. Thank you for watching High Peak Education.